Okay. So the first thing is this week in lab, you're taking the lab exam, the first lab exam. Okay. And if you can't make it to your lab for it, see if you can make it to one of the other 3 labs. Okay. I have 4 lab sections a week, so look at the syllabus and see if that'll work for you. So lab exam 1 is going to be in lab this week. And so you should be ready to answer questions like the questions that we've done on the lab worksheets. And so I would recommend going back to go back to your lab worksheets and go back over those problems and make sure that you know how to answer those questions. Yes?
So will that be today then for Monday lab?
Yes.
Okay, and how long is it?
It will not be super long. I would say you'll be, I don't remember exactly, but everyone will be done within an hour, I think. Yeah. Any other questions? Okay. Now, I gave you some 2-dimensional kinematics problems to work on, right? I think. Anybody have any questions about any of those? You want to see me go over any problems from the homework or anything like that? Okay.
Can you go over 4B?
Sure. From 2D kinematics?
Yep.
The basketball one?
Yeah.
Oh, yeah. Okay, it's a displacement thing. Okay, so all right, so it says that so this basketball is shot, and we know the horizontal distance. Like the idea is we know the person standing on the free throw line, so it's 15 feet from the basket. And we know the speed and the angle, say we're measuring that with a video or something, but somehow we don't know the height that it's being thrown from, so we're going to calculate what the height is. I cannot remember what that height is, but I think it's 1.87 maybe.
1.86, I think.
Okay. Okay, so 1.86 meters. So, and then it says, what's the displacement vector from the point where the ball is shot to the ball's highest point? Oh, actually, it doesn't, you can do this problem and get the right answer, part B, without even knowing where it's shot from. But anyways, so let's do part B. Okay, so this ball is shot from a height of 1.86 meters. And when it starts, it makes an angle of 60 degrees with the horizontal, I think, 60 degrees, and 7.8 meters per second is the speed. And so it follows a trajectory like that. Ooh, that's such a good parabola. And so it goes through the basket up here somewhere. And we're trying to figure out the displacement from where it's thrown to where it is at the highest point. So in order to do that, remember the displacement vector is the final position minus the initial position. So our final position is going to be where the ball is at its highest point, and our initial position is going to be when it's thrown, when it's shot. And we have to choose a coordinate system and stuff. I'm going to choose the one I always choose. Boring is good. The more boring you can make this, the less likely you are to make dumb mistakes from one problem to another, you know, because you just are used to writing down the same stuff. Okay, so our time equals 0 instant is going to be the instant that it's thrown, that it's shot. And our time final is going to be when it reaches the highest point. We don't know how long it takes. We know the acceleration vector is 0, negative 9.81. The initial position is 0, 1.86, based on where I put the origin. P final, we don't know anything about yet. We're trying to get both of those. So we're trying to get this vector. V initial is 7.8. That's the speed times the cosine of 60 and the sine of 60. Can someone multiply those two out for me? What's 7.8 times the cosine of 60? Oh, I can do the y one. That's 3.9. Yeah.
3.9.
That's the sine. Oh, yeah, you're right. I'm thinking of 30. So 3.9.
60 is 6.75499.
So I'll just call it 6.75. Okay. And then the one thing we've been waiting to say, since it's the highest point, is we know that V final is equal to 0. V final y. So we can find PFY using this equation. So 2AY times the quantity PFY minus PIY is equal to VFY squared minus VIY squared. So 2 times negative 9.81 is 19.62 times PFY minus 1.86. And then that's equal to 0 squared minus 6.75 squared. So PFY minus 1.86 is equal to, what's 45.56 negative divided by negative 19.62. Can you divide that out too?
Uh, 2.322.
2.32. And then, so PFY is this plus 1.86. So that's 0.06, 4.18 meters. Okay, so there's the y component. We need to calculate the x component too. So for the x component, there's not an equation that works. So the first thing we have to do is calculate TF. So no equation works for PFX. So find TF. And we can do that from this equation. VFY is equal to VIY plus AYTF. So 4.18 is equal to 1.86 minus 9.81 TF. So 9.81 TF because hold on. I'm putting in velocities instead of positions instead of velocities. VFY is 0. VIY is 6.75. And so 9.81 TF is equal to 6.75. And so what's 6.75 divided by 9.81?
0.688.
So 0.69 seconds. And now we can use that in this equation. PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 3.9 times 0.69, and then AX is 0, so that's 0. And what's 3.9 times 0.69?
2.691.
2.69. Okay. So together, these things tell us that PF as a vector is equal to 2.69 4.18. And we already knew that P initial is 0 for X, 1.86 for Y. And so the displacement vector is 2.69 4.18 minus 0, 1.86, and that is 2.69 2.32. Any questions about that? Any other homework questions you'd like me to go over? Okay, well, for the next couple days, we're going to be just kind of setting up the next topic. And in the meantime, I'll be having you work on 2D kinematics problems. But I'm just going to be sort of explaining, defining new terms and stuff as we get towards Newton's second law. So the next topic that we're doing is 2D kinetics. Of particles. And kinetics means combining kinematics with the causes of the motion. And for now, we're going to think of the causes of the motion as mass and force. So those are two new things that we're dealing with. For kinematics, we only were dealing with time, position, velocity, and acceleration. Now we're going to combine it with this. In And where we're heading is the most important equation in this class. And that's Newton's second law. And Newton's second law says if you add up all the forces acting on an object, so I'm going to call that F net, the sum of all those forces is equal to the mass of the object times the acceleration of the object's center of mass. So this is the sum of all forces on the object m is the mass of the object and this is the acceleration of the object's center of mass. Well, as long as we're doing particle stuff, we're always treating every object as if it just exists at a single point. It doesn't have any length dimensions or anything like that. And so we're always treating objects like the only point that exists is their center of mass. So to us, we can think of this as just the acceleration of the object. Okay. And I'm sure, this is a famous equation that's kind of everywhere enough that you've probably at some time heard F equals ma, even if you've never taken physics or anything. So that's what we're heading towards. But before we can get to this equation, let me point out that, so you see the two causes of motion in this equation, mass and force, but you also see acceleration, which comes from kinematics. So this is the equation that lets us connect the causes of the motion to the motion that it produces, okay? So what we're going to get into is this object has this mass. If I kick it this hard, where's it going to go? That's what we're heading towards, okay? So the first thing I have to do is define the mass and define the force. Mass is sort of the simpler one of the two. And the definition of mass that I'm going to give you is that it measures an object's resistance to acceleration. A lot of people have get into the habit over your lives of thinking of mass and weight as the same thing. This is related to weight, but they're not the same thing. So it's not the same thing. Weight is the force that gravity applies to an object. And mass is how hard it is to accelerate an object. Okay, so think of these two football players running towards each other. Okay, what's going to happen when those two collide? Okay, while they're running with a constant velocity towards each other, there's no acceleration. Acceleration is when velocity changes. When they collide, there's going to be some drastic changing of velocities. But which one of these is going to have their velocity change the most? The small guy. The big guy is going to basically keep moving in the same direction. He'll slow down a little bit, but the acceleration won't stop him. You know what I mean? The little guy is going to go exactly back the way he came. Like his acceleration is going to be huge. And the reason for that is the big guy has a mass that makes him much harder to accelerate than the small guy. Okay? Okay, well, what about the weight? It's related to the weight. You measure weight like on a bathroom scale or whatever. And obviously the person with more mass, the bathroom scale says that they weigh more also, you know. But if you took these two out into space, okay, and launched them towards each other, well, first, before you launch them towards each other, you put them on a bathroom scale, okay? And so this is not possible, but say we're far enough out in space that they don't feel any gravity, okay? Well, if you put them on a bathroom scale, what is the force that gravity is going to apply to them? Zero. They don't feel any gravitational force. But if you launch them towards each other, the same thing is going to happen in space as happens on Earth. The person that has more mass is going to keep moving basically the way they were going, and the smaller person is going to accelerate a lot. Okay? So you have, every object has an amount of mass, and that is totally independent of gravity. Gravity can change depending on what planet you're on or whatever. Okay. In fact, when people are living on space stations and stuff, there's a big problem of them losing muscle mass and bone density and stuff like that. So they need to be weighed carefully all the time to make sure that they're not having a problem with this. But in a space station going around the Earth, there's no detectable gravity. Basically, you're in free fall around the Earth all the time. And so you can't use a scale to weigh somebody. It would say zero weight. Okay? So how do they measure someone's weight? Well, they don't measure the force gravity applies to them. Instead, they put them in a machine that shakes them with known forces, and they measure the acceleration that goes along with it. Okay? And so from that, they can tell very precisely how their mass is changing. So they're not measuring the weight, they're measuring the mass. Okay. Notice, first, the units. SI units for mass are kilograms. So that's what we're mostly going to use for mass. And one thing I want you to remember is that pounds, you know, every bathroom scale has a switch on it where you can look at your weight in pounds or you can look at it in kilograms. Well, actually, the scale can't measure your mass. It can only measure how hard gravity is pulling on you. So it makes the assumption that you're only going to use their bathroom scale on the surface of the Earth. And if you're on the surface of the Earth, then it can tell you what your mass is in kilograms based on how hard it knows things on the surface of the Earth are being pulled down based on their mass. Okay, but if you use a bathroom scale on the moon or something, the gravity in the moon pulls a lot less hard on you than the gravity on Earth. Okay, so when you stand on the bathroom scale, it'll say 20 pounds or something, 30 pounds. And that's an accurate measure of the weight, okay? But then if you switch the settings to kilograms and it would say that you have a mass of, say, 15 kilograms, something like that. And that would be wrong because it's assuming that you're using the scale on the surface of the Earth. It can't measure your mass directly. It can only measure the force. Okay, so pounds are actually a unit of force, not mass. And the last thing I want to point out about mass is notice this. Mass is a positive number. Not a vector. If you think about like somebody having a certain mass in a certain direction, it doesn't make any sense, So mass is just a positive number that just gives a scale for how hard it is to accelerate something. Look up here at this equation. We'll talk about this more in the next couple of weeks. But look at Newton's second law and notice that the acceleration vector is multiplied times the mass. Well, if the mass is positive, what do you know about the directions of the acceleration and the net force? Like, think about the rules of multiplying a vector by a number. What happens to the vector when you multiply it by a positive number? Yeah, it can get smaller too, but what it does do is stay in the exact same direction. Okay? And so Newton's second law says an object's acceleration is always in the same direction as the net force vector. Okay, so now let's talk about the one of these that's a little more complicated, force. So mass is a number, but force is a vector. That measures the intensity and the direction of a push or a pull on an object. The units of force, let's just do the SI units. The SI units of force are a really ugly thing. Kilograms times meters per second squared. But since we're going to use force all the time, and this is sort of an ugly unit, people just give it its own name, the Newton. And it's abbreviated with a capital N. So 1 Newton is 1 kilogram meter per second squared. In this class, there are only two ways that forces are going to occur. So let's say there are only two ways forces arise. The first one is gravity, that's the weight force. And the second force is contact between the object and its surroundings. If you're talking totally generally, we're not going to talk about this in this class, but there are some other types of forces that would fall into this same category as gravity. Those would be like magnetic field forces, electric field forces, anything that doesn't directly have to do with contact between objects. But in this class, we'll just represent that as gravity. Okay, anybody have any questions about just the basic definitions of mass and force? So force is a vector, mass is a number. Well, the next thing that I'm going to do is just start talking about various types of forces and what we know about them. Okay? So first, let's talk about the weight. That's the force applied by gravity. Well, I showed the video of the bullet and the bullet being dropped and the bullet fired. And what we saw is that horizontally, no matter what the object's doing, gravity pulls just as hard on the object. Okay? And so I'm going to start by making the assumption that the force gravity applies to an object is the same no matter what the object is doing. Okay? And now, then we're going to think, is there any way we can figure out what that force is? Okay, so can we figure out what the weight force is? And so what we're going to do is we're going to think of a 1 kilogram object that's in free fall. So a 1 kilogram object in free fall. It's not touching anything, so the only force on it is weight. So weight is the only force on the object. And what do we know about the object's acceleration?
-5.3.
Yeah, right. So, so if we go to Newton's second law, the net force is just the force of gravity. Nothing else is acting on it, so I'll write it like this. Okay? And that is equal to the mass of the object, which we said is 1 kilogram, times the acceleration of the object, which is 0, negative 9.81. And so our force, our gravitational force, is 0 in the x direction and negative 9.81 newtons in the y direction. So it's just a downward force of 9.81 newtons. Okay, so maybe every object has a weight force applied to it that's just equal to 9.81 newtons. Okay, so let's try something with a different mass and think about it the same way. Think about it in free fall. So now think about a 10 kilogram mass in free fall. The only force acting on it is the weight force. And Newton's second law says that net force is equal to the mass times its acceleration. And if it's in free fall, we know that objects of all different masses fall due to gravity downwards at 9.81 meters per second squared. And so here we got that the gravitational force is 0 for x, negative 98.1 newtons for y. So gravity is pulling harder on the heavier thing than it is on the lighter thing. Okay, so the final answer is, and I think, you know, if these two examples make sense, then the final answer will make sense. So in general, for an object with a mass of m, the gravitational force vector is 0, negative 9.81 times m in the y direction. Or 9.81 m down. Well, now if we call positive 9.81 meters per second squared the constant g, lowercase g, then the gravitational force is mg down. Okay, so the force gravity applies to a thing is proportional to the mass, and it's always pointing straight down. Well, that's a pretty great start. Like just reasoning through the stuff we already knew from earlier in the class, we were able to figure out what the force is that gravity applies to objects of different masses. Okay? So now that we know the force that gravity applies to things, let's see if we can use that to figure out some other forces. Okay, let's say that there is a 100 kilogram man standing on a scale. What's the force applied to the man by the scale. So this scale is just on the floor. Here's the man. This is the scale. Well, now what's the net force? Now there are only two things acting. I said that the only forces in this class are going to be the weight force and then forces from things that are touching the object. Well, now the scale is touching the man, right? So F net is just equal to the weight force, the force of gravity, plus the force of the scale. And we've figured out what the force of gravity is. We said that the man's mass is 100 kilograms. So this is just going to be 0, negative 981. And then we're trying to calculate the force applied by the scale. So Newton's second law then says 0, negative 981 plus the force applied to the man by the scale is equal to the mass of the man times his acceleration. If he's just standing there not moving, what's his acceleration? 0. So this is the acceleration vector. And so if we simplify, we get 0, negative 981 plus F scale is equal to zeros. You can think of this as two separate equations, an x equation and a y equation. So the x equation says 0 plus the x component of the scale force, and that's equal to 0. And the y equation says negative 981 plus the y equation of the scale force is equal to 0. So do the algebra, and what you get is that the force applied to the man by the scale is equal to 0 for x, positive 981 newtons for y. Or in other words, 981 newtons up. So that is why a bathroom scale can tell you how much you weigh, because if you're standing on a bathroom scale and not accelerating and not touching anything else, the force that the scale has to apply to you is your weight. Okay? Well, what if you are accelerating? I mean, you know what happens if you jump off the sink onto a scale. The numbers go spinning. That's because when you land, there's an acceleration. And so the scale is trying to measure a weight or trying to measure a force that is not equal to your weight. It's something a lot bigger than your weight, just temporarily. Same thing if you're like, I want to weigh less, so you hold on to the towel rack or whatever, then depending on how much force you put into the towel rack, the scale will tell you you weigh 60 pounds or whatever, but that's not measuring your weight because you're splitting up your weight between the towel rack and the scale, you know. Anybody have any questions about that calculation or that thought process? Okay, let's do another example related. Now the same guy, the 100 kilogram man, let's say he's on a scale that's on an elevator. Accelerating up at 2 meters per second squared. What's the force the scale applies to the man in this case? Okay, so now here's the elevator. There's the scale. There's the man. And everything on here is accelerating upwards at 2 meters per second squared. Okay? Well, what forces are acting on the man? There's the weight, and then there's the scale pushing on him. And nothing else is touching him, so we know those are the only two forces. Okay, so F net. Oh, hold on a sec. Okay, so F net is equal to the weight force plus the force applied to him by the scale. And so now we'll go to Newton's second law. And we have that 0, negative 981. Plus the force applied by the scale is equal to the mass times the acceleration. This time, since the scale's accelerating, the man is also accelerating. So how would I represent the man's acceleration as a vector? It has a magnitude of 2. It's pointed up. So what would that be in components? Here's your coordinate system. 0, 2, that's right. So if this is your coordinate system, the acceleration is straight up with a magnitude of, this vector has a length of 2. And so the coordinates of that point tell you the components of the vector. And so it's 0, 2. And so the two equations, there's an x equation that says 0 plus f scale x component is equal to 100 times 0. And the y equation says negative 981 plus f scale y component is equal to 100 times 2. And if you solve these two equations, you get that the force applied by the scale is equal to 0 for x and 200. So 1,181 newtons in the y direction. Or in other words, 1181 newtons up. So would that really happen if you're standing on a bathroom scale on an elevator and it starts to accelerate up? Would the weight reading on the scale really go up? Yeah, it would. And you can feel it in your legs on an elevator when you start to go up, just briefly until it gets up to its constant speed. You feel your legs have to work a little harder to support you. And when it starts accelerating down, you can feel yourself, you feel lighter. And that comes from the opposite of this, which would say you weigh a little less. The force applied by the scale is a little less when you're accelerating down. Any questions about that yet?
Is it the same thing as like when you're in the car and going over a hill?
Yeah, that's right. Yep, exactly. Yeah, so anytime you're accelerating in the same direction as gravity, the acceleration makes you feel a little lighter. And anytime you're accelerating opposite the direction of gravity, it makes you feel a little heavier. So like when people are in a spaceship accelerating up, they feel really heavy, you know? And the limit of it is if you're accelerating down at free fall, if you're falling, jumping, whatever, there's nothing touching you and you don't feel any force on you at all. Okay. Let's just go with that for today. Let's stop. It feels like just a lot of information. It's not going to be as bad on Wednesday. We'll get back to some sort of less talking and more doing stuff. So, okay.